Today we're going to be going through a tutorial for HAMS, or Hydrodynamic Analysis of Marine Structures, which can be found by, just do like HAMS Enro. It's GitHub by Yingyi Liu, HAMS. This is a boundary element method software to calculate some hydrodynamic coefficients that we can later use to simulate the dynamics of a floating platform like this offshore wind platform right here. So the first step is we need to create a .gdf file from Rhino. This .gdf is going to be our mesh file. So our actual platform is going to be meshed into quadrilaterals, and then HAMS is going to use that for the analysis. We need to create a .gdf file in Rhino because we need to use the mesh converter to go from .gdf to PNL, because .pnl is the format HAMS uses. If you have an STL, so for example, if you use something like SolidWorks and you like to get the GDF or PNL, you could use something like Mesh Magic just to convert your mesh from an STL to a .gdf, and they have some other options for that as well. But Rhino is just like SolidWorks. It's another 3D modeling software. You can come to just like this website. I believe they have like 30-day free trial for students, but come here, download it, do all the necessary steps, and then once you open it up, you're going to be met with a screen like this. So we're just going to be doing a simple spar geometry. So up here, we can go to Solid Tools, come over here to the left, click Cylinder. For the base of the cylinder, we're going to be 0, 0, 0. Radius 3 is fine. And the end of the cylinder, we can pick somewhere, just like maybe down there. That should be fine. And so for HAMS, you only want to model the submerged part of the platform. So even if there was a significant portion above the waterline, we don't model that when we use HAMS, only the submerged part. And it's going to assume that z equals 0 is the waterline. So it's going to assume that this face right here is going to be our water plane mesh. And so once we have our solid, we can come up here to Mesh Tools, click this button right here, third from the right, Quad Remesh. We're going to select our object. We're going to do 750 quadrilaterals, so pretty much we're going to decide how many panels we want to break this solid up into. Obviously, increasing this quad count is going to make the HAMS simulation time longer. So you really want to find a balance between accuracy and how much time it's going to take to actually run it. But 750 should be sufficient for this tutorial. Unclosed. Okay, there we go. So now we can come up here on this right and click this yellow box, and we're going to select the mesh. So we can see it looks a little weird when it has the solid and the mesh, but if we click that, we can see that our mesh is indeed there. So now with that mesh selected, we're going to go to File, Export Origin. The base insertion point, we just want to use Enter. We want to use this world origin since we defined it about 0, 0, 0. We're going to call this Spar Simple.gdf. Come down here, you can scroll, see all the ways you can save it. We want to go to WAMIT GDF. And then we're going to just do... we're just going to export. If it's symmetrical about any planes, you can select it here, and then you actually go to run HAMS, it'll pick up it has symmetry, and then you could essentially half the number of quadrilaterals you need to use. So if you have a rather large and intricate structure, this is definitely something you'd want to take advantage of. Clicking Enter, we can see we've successfully wrote 727 faces to this .gdf. And so that's going to be it for this Rhino section. We have our .gdf. Now we're going to be working on using this mesh converter to convert from a GDF to a PNL. But first, we're going to download HAMS from the GitHub directory. Something that's going to be really handy with this whole HAMS tutorial and boundary element stuff is going to be a software called BEM Rosetta, which you can also find on GitHub. This is just very helpful in viewing the meshes you create, viewing the hydrodynamic coefficients, and it's actually pretty handy in converting different types of files. between the different boundary element method software. So for example, when I'm at HAMS Nemo, and you can save it as a bunch of different times as well, or even the OpenFAST HydroDyn.dat. We come here, we can just to releases. We just download the .exe. And if we could just say, just put on this desktop also, we can run this. Okay. And we have a bunch of different options up here. You could link your boundary element method solver to this, so you can just run it through Rosetta if you like. It doesn't really matter too much. Viewing the hydrodynamic coefficients, which we'll look at later. But then also there's this mesh viewer. So you can we can drag and drop our .gdf we created in Rhino into here, and we can kind of just examine it, make sure all these surface normals are pointing outwards like they should, and then make sure everything is looking good and closed. Okay, so if we go back to here, we need to use the HAMS mesh converter to convert from GDF to PNL. But first, we need to actually download HAMS and create a directory for the project. So if we just come to here, and just Google HAMS NRL again, come to GitHub, code, download zip. And we can just drag and drop that to here. We're going to just extract it here, or wherever you'd like. So now inside this folder, we have HAMS master. We have a couple important things like cert test, mesh converter, which is where we're going to be looking at. But let's first just create our new directory. So we come to the cert test, we can see an example. We have 4 examples of different platforms. We're just going to take this deep sea wind. We're going to Control-C, Control-V, create a new thing. We're just going to call this simple Spar. So now we have a folder where we're going to be putting our mesh after we convert it, and updating some other things as well. But going back to the mesh converter, the important file is the settings.ctrl. So this is how we control what the mesh converter is going to do. So it reads from top down, has gravity, acceleration, the density, the name of the mesh file. So note that this / just means that the mesh converter is going to be looking for that GDF file in the same directory that you're running this .bat from. So it's going to be looking in the directory for the GDF. So we can take that, post that to GDF. Sometimes it has issues with capital letters. Same file, but lowercase. We're going to change this to Spar simple .gdf, just like it is here. The center of gravity you can set for your platform. I think we can estimate that to be around -10 in the Z direction. And the center of rotation, which is typically the centroid of your water plane area, but 0, 0, 0 is accurate for the simple cylinder. So save that. We're going to run this .bat. And we can see it's successfully converted from the GDF to PNL. And you can see a lot of stuff like volume, the mass, the stiffness, and the 3 principal directions, and also the rotational inertia of the platform as well, which is important if you want to use this in like OpenFAST, and it's handy that the mesh converter just gives that to you. So after we run that, we're going to be getting 3 new files in here, mainly whole whole mesh.pnl, waterplane mesh.pnl, and this hydrostatic.in. So whole mesh PNL, we can actually examine it here. Similar to our GDF that we created, except now we can notice there's actually no waterline mesh. It's actually an empty face right there, an empty surface. We do that because we create a separate mesh just for the waterline itself. So we need both of these two files in the HAMS analysis. So we're going to take these P&Ls, we're going to copy them. We're going to go back to our folder that we just created, simple Spar. We go into the input. We can see there already a whole mesh.pnl and a waterplane mesh PNL. We're just going to overwrite those with ours. And so then what we need to do is we need to update this hydrostatic stiffness configuration file, which is this hydrostatic.in right here. This is in our simple Spar geometry. And it has a couple of different matrices, like your body mass matrix. For example, these three values are just going to be the mass of the platform. And these values right here correspond to the inertia of the platform. So your body mass matrix is mass, and then IXX, IYY, IZZ, along with the cross degrees of freedom. You can add external linear damping or quadratic damping matrix. It actually looks like this has some external quadratic damping, so we're going to just replace that with all zeros. The hydrostatic restoring matrix, which we're going to be able to just get from the mesh translator, and an external restoring matrix, but again, this should all just be 0. Typically, this is used to include a mooring system, which can be simplified and linearized into, additional spring constants that you could add in here. But we're going to ignore the mooring system for now. So going back to the mesh translator, or converter, it also generated an additional hydrostatic.in file. If we open this one up, we can see that it only has its two matrices here. So it has its mass matrix and restoring matrix. So we're going to take this mass matrix and we're going to copy and paste it into this mass matrix. And we're going to do the same thing with the restoring matrix. And we're going to make sure that the center of gravity and everything is set correctly. Great. So the majority of the work is done. Now we just need to come into the final HAMS settings. So if we come here, we need to update the actual HAMS settings itself. So input, this control file.in, that is where we decide things like how long we want the simulation to run for, how many frequencies and such. So we can pick a water depth of -200. If it's negative, it just means it's in deep water, so keep that in mind. 0 and infinity frequency limits, we want to set this to 1 because we need that A infinity and A 0 if we'd like to do some modeling in like OpenFAST or something. If we'd like to continue to use something in like OpenFAST, we want to make sure the input frequency and output frequency are the correct values. So for an input frequency type, we want wave frequency in rads per second, and the output we're going to set as 4 because we want an output as wave period because that is what OpenFAST is expecting. The number of frequencies we want to do is around 100. So 100 frequencies starting at 0.05, incrementing by 0.05 is normally sufficient for the majority of structures. But if something is smaller, maybe you need to go up to higher frequencies, and you can see it as such. For the number of wave headings, so each direction gets its own simulation or calculation. So if we use these 5 degrees, we'd have hydrodynamic coefficients for each wave heading. So for a 0 degree wave heading, and then a 45 degree, and then 90. And we'd have separate coefficients for each one of these directions. For now, we can just do one heading, which we will say will be the head C's at 0. Reference body center, don't touch too much of these too much. If you know how many threads you have on your computer, you can modify this value to run in parallel, which really speeds up the HAMS computations. So that's something to keep in mind as well. There are a couple different solutions or approaches to calculate the wave diffraction forces. So you should look at the HAMS paper to figure out which one is used and the theory behind that calculation. So we can save that, and then we're ready to run HAMS. So we're going to go to this run hams.bat. We're going to click it. And now we can see that it is going through each of the frequencies we specified. And since we used only 750 panels, this is going to be rather quick. And so now our computation completes successfully. Great. So now we're going to use, again, BEM Rosetta just to kind of view some of these coefficients that we just calculated. So if we go into output, WAMIT format, we have a bunch of these different files, and these actually hold the information to our hydrodynamic coefficients. So for example, I think the .1 is added mass, 3 is excitation, HST is your hydrostatic stiffness, and one of these is your damping. So if we come up here to hydrocoef, we can just drag and drop these right into here, and it's going to automatically look in this folder, find all the files, and allow us to look at all of the hydrodynamic coefficients like A, B, the excitation, and the stiffness as well. But this is not a function of frequency, so this is just static. So we can see here all the additional coefficients for each direction and each cross degree of freedom. So we have a pure heave, a pure surge, but we also have a contribution of a heave added mass force due to a acceleration in surge, which would be this. So added mass surge heave, that'd be the equivalent of a subscript 1-3 because it's surge and heave, and it's symmetrical. So if this was 1 heave surge, it'd be the same thing. And then we can look at the same with the damping and the excitations as well. This is the impulse response function that solves for the memory effect, the convolution, the Cummins equation, which is something to just take note of as well. If you don't need all these cross degrees of freedom, because sometimes they just get in the way since they're relatively small compared to the main degrees of freedom. So you can just come up here to go to options, high degree of freedom cross coupling. And when you come back, you'll have only your pure direction hydrodynamic coefficient.